All right, so today we're going to be talking about recursion, which is a very scary topic. I think it's one of those topics where kind of like object orientation requires you to think in a way that's different than you are typically thinking about solving problems. So um, it's it's a new way of thinking, and anytime you encounter something like that, it takes a while to get used to. So I wouldn't, if you don't already kind of know how this works, I wouldn't expect to just get it instantly. If that happens to you, then that's wonderful. If not, then just kind of, you're going to get a couple of exposures, um, and just kind of roll with it. Okay. So can anyone tell me anything about recursion?
Isn't it like a function call, a function calls itself inside of that function, right?
Yeah, exactly. So recursion is, a recursive function is one where it calls itself. So we can write a recursive function. So def is this legal in Python? Can I do this?
I guess we'll find out.
Yes.
Okay, so I can't do this. Is anything gonna am I gonna get an error or anything like that?
Will it be an infinite loop? I mean, it won't print anything, but it's gonna just call itself infinitely, right?
Yeah. In theory, it will call itself infinitely. Let's see. So what actually happens is not quite an infinite call. So what is the error that I'm getting?
Max depth exceeded.
Stack. Yeah.
Yeah. Yep. So it says recursion error. So that's a specific error built into Python. Recursion error, maximum recursion depth exceeded. So the error is maximum recursion depth exceeded. And then I get a stack trace, but the stack trace is not all that helpful. Sorry, 1 second. Okay. So the stack trace is not going to be that interesting because it's the same. It's saying I'm trying to call recurse here on line 2, which is being called by recurse, which is being called by recurse. So this traceback is just going to be basically the same thing, and it goes on up. And the first one here, this line 5. So this line 5 is starting it off, and then we're getting an error somewhere on line 2, but it's happening a lot of times. So what is maximum recursion depth? Why not just keep going forever?
Does it do that to prevent the program from crashing?
Yeah. So if I kept, so for example, if I instead of this, I just wrote like an infinite while loop. So while true, I kind of have to do something here, but I could also have an infinite while loop that will run and run and run and run, but it won't throw an error, right? It'll just keep running. So they're both of these are, infinite programs, but only this one throws an error in Python.
Can Python detect that it's recursion and it treats it differently, or something of that nature?
Yeah, so that's a good question. So there's a little hint here. Says previous line repeated 996 times. So what's happening is that Python has a default configuration which you can change, but it only allows you to call a recursive function 1,000 times, or not even a recursive. It allows you to have 1,000 things on the call stack before it throws an error. This is somewhat arbitrary. It could be, could be more, could be less. But that's what it is. So a while loop, if I go back here, my while loop, how many call stacks is this going to create? This program, if I ran just this program.
I mean, an infinite number.
Okay, so we can take a look. Let's go ahead and take a look. So I'm going to use the debugger here, and I think I should be able to do this. So I'm just going to use the debugger so I can walk through step by step here. So this doesn't really look like anything's happening. It's not a very interesting program, but it is running over and over again. So it's just assigning x, or assigning 10 to x over and over and over again. And my call stack here, we'll see more of this in just a second, but there's actually only just one call stack here. So it's not creating, so this is why Python doesn't throw an error for this particular infinite program. Because it's not creating a new call stack every time. It's just, there's one call stack and it's just cycling through. So it's kind of reusing that same call stack again. If we go back here to this program now, and we take a look at that, and I'm going to run this in debug mode. And if I run this, look at what happens to the call stack. So I keep calling it, and the call stack is just getting bigger and bigger and bigger. So the call stack. Let's talk about the call stack. So the call stack, for one, is a stack data structure. So we had a couple groups talked about this last week. So what is a stack?
Pancakes.
Pancake, yes. You can have stacks of pancakes. You can have stacks of plates. You can have stacks of I don't know, 45-pound plates.
Isn't it how the returns of the functions that you run or process, was it first in, last out? Or right? Isn't that right?
Yeah. So it is first in, last out. So it's like, you have a stack of pancakes, right? So if you're eating, it's not the best analogy because you can cut through all of them. So a stack of plates at the buffet. I think this is my favorite analogy. So stack of plates at the buffet. If I see a bunch of plates at the buffet, I am going to grab the one that's on top of the stack, right? So I grab the plate that's on top, I use it, whatever, and then when the employee comes and puts more clean plates on the stack, they're going to put it right on top, right? So there's only ever one access point. So people are only ever putting things on the top or taking things off of the top. And if I start with nothing and I put a plate on, and then another plate on top of that, then another plate on top of that, and if I want to remove them, I remove the most recent one first, and then this one, and then the last thing that I remove is the first plate that I put on. So it's that's the data structure called a stack, and your call stack when you're running the program is basically you have a stack keeping track of what's called when. So it's a way for the environment that's executing your code to keep track of what's happening, where it is in the program. So let's take a break real quick from the recursive stuff, and let's just look at a normal function. So I'm going to have def func1 I'll return a value here. Let's do one result. Do something like that. All right. So now I'm going to call func2. So someone walk me through what's going to happen here with this program. Let me call on someone. Let's go with Celine. So Celine, where is this program gonna start?
So I think it will return func1. Also func2, right? So f1 is equals to it will call function1, and then function1 will return the function1 string,
Okay.
and then it will print it.
Okay, good. So it's actually, so it's gonna start here. So here's where everything, I'm just defining things. So nothing is really happening here. Here's where I kind of set off the chain of events. So I'm gonna initiate some action here by calling this function. So I'm gonna call func2. Func2 needs to call func1. Excuse me. So func2, in order for func2 to finish, func1's gonna have to finish. So we have this, I don't know, maybe contradiction or tension, where func2 needs to return a result. So func2, its mission in life is to execute itself and return a result. However, it's dependent on this, right? So func2 it can't really just do all of its work on its own. It has to kind of pass off something. It has to say, okay, func1, I need you to return. And once you return, then I can use that value and then I can return. So what does that look like on the call stack? So we start with this, basically, you can think of this as like the default call stack. This is like the initial execution context. And I'm going to call func2 now. So I've called func2, and what happened to the call stack?
Function 2 was added on it.
Yeah. So function 2 was added on it because, you can think of let's say the default execution context as kind of a function call in a way. But so you have this default execution context, and this default execution context can't finish, right? It can't finish until func2 finishes. So how do you mark that? Well, you create a new stack frame. So these are called stack frames. It doesn't really matter, but they're basically objects. So this stack frame is an object that contains information about its execution context. So you don't need to worry about the details, but that's what it's doing. So I'm calling a function, which means I need to create a new execution context or a stack frame. So I create a new stack frame and say, okay, well, I'm gonna need some stuff from func2. I need func2 to execute here, and then once that executes, I can pop it off of the stack. I can remove func2 off the stack once it finishes executing, and then I can continue on with the previous execution context, which in this case is our kind of baseline execution context. Okay, so I've now called func2, and then what happens on line 6 though? Well, line 6, I call func1. So that means I'm going to get another execution context. I'm going to add another stack frame here because func2 can't just finish by itself, right? It doesn't have the resources within itself to finish. It has to kind of defer to func1. So we create a new stack frame for func1. So func1 has its own execution context, and in this case, it can execute without any other like external dependencies. So func1 can execute. So if I keep stepping through, func1 is going to execute, and when it finishes executing, when it returns, it's going to this call stack will have served its purpose, right? This call stack will be all done. Sorry. So this call stack will have served its purpose, and then we can move on to right here. So this call stack will get removed, and this value that's returned will be assigned here within this call stack. So I'm going to pop this off. And I can see, sorry, let me see if I can make this visible. Okay, so I can see here that the return value from func1 is func1. Okay, so I've function 1 is finished executing at this point, right? So this is finished executing. This gets assigned to func1 res. So I can see, should be able to see that if I hover over it. Let me just go down one more. So f1 res, I see this local variable now equals func1, but I'm still in this function is still not finished executing. So this call stack is still active. Once I click through again, this line is going to execute, and none is implicitly going to be returned from func2. And once that happens, then I don't need that call stack anymore. So it gets popped off. So this func2 execution context gets popped off once it's done executing. And then I come back here, and then I have, I'm done calling functions. So there's no more, there's nothing on the stack. So I can keep executing. And in this case, there's nothing left, so it'll just exit. But if there were more functions or more things happening, it could just keep adding things onto the call stack and then popping them off as they get as they finish executing. So that's that may be a lot of information. You can play with it yourself in the VS Code debugger. So I would encourage you to play around with that. It's a nice kind of visual tool for understanding, the nitty-gritty details of how your program is executing. Are there any questions about that?
When you got none, because right towards the end for the function 2, is that because it says print instead of return?
Yeah, so in Python, if you don't explicitly return, it basically will just add this in automatically.
Okay, that's what I thought.
Yeah. Okay, so now let's go back to our recursive example. So if I execute this now in the debugger, what's going to happen is it's just going to keep creating stack frame after stack frame, and it can never resolve. It never reaches completion because it's infinite, right? There's no way for this program to stop other than the Python interpreter deciding, hey, you probably didn't mean to do that. So I'm going to go ahead and throw an error for you. If the Python interpreter didn't throw an error, then eventually you would run out of memory, because you're continuing. Each one of these is like an object, so you're like creating object after object after object after object, and eventually you'll just run out of memory. So that's one reason why the Python interpreter will stop you. So when you're writing, when thinking about recursive functions, this is kind of the absolute minimum, but it's not really enough to do anything useful. So the minimum requirement is that the function has to call itself. But if you want to do something useful, then you also have to figure out a way for it to stop calling itself. So you need some kind of condition for the function to stop calling itself. So it can stop calling itself, and then all those stacks that it's built up, however high they are, they can get popped off, right? So when we write recursive functions, we need what's called a base case. A base case means once this condition is satisfied, then I'm done, or I've reached the end of what I can do here, and I'm going to stop executing. I'm going to stop recursing. So let's take a quick look at that. So we're going to write a couple simple functions or programs. They're going to do things that we typically do with for loops or some other form of iteration. We're going to do it recursively. So the first thing is we're going to count. Let's count up. Let me see. Actually, no, we're going to count down. I think that's the easier one. So if we were to count down from a given number, let's say write a function that takes in a number. So def count down is going to take in a number. And then if we're going to write this normally or iteratively, we would do for something like, well, how might we do this?
So recursively, what our base case would be 0.
No, let's do it iteratively.
Oh, non-recursively? Okay.
Yeah.
You could just use a counter.
Or I.
Okay. So we could use a counter. We could use a while loop or a for loop. I think either one could work. Let's just use a while loop for now, I think. So counter. So we'll start at 0, let's say. So while let's see, less than num. Oh, actually, this would be counting up. So we'll print. Should we do counting up? Maybe we should do count up. So, sorry, give me 1 sec to think. Yeah, so we'll do countdown for now. Okay, so while we don't actually need a counter variable, we can just start with one less than 0. So I'm going to print num. So we start off with 10. And then I'm gonna subtract 1 from num. Okay, so let's see if that works. Okay, so we're counting down from 10 to 1. So we can, there's a couple ways we could do this. This is, this would be like a standard iterative solution that we should be familiar with. Okay, we could do it recursively. So when we think about recursive solutions, we need to think about 2 things. One is the base case, and the other thing is the recursive case. So base case, and then recursive case. So the base case is where we need to stop recursing so we don't get ourselves in an infinite loop. And the recursive case is what's going to happen otherwise. And our goal in the recursive case is to get us closer to the base case. So we have some problem domain, like in this case, it's a number. And we want to get it, so we want to somehow break down our problem 1 step at a time until we arrive at our base case. So what is our base case? If we want to count down from a given number to, let's just say 1, what is our base case going to be?
Num is equals to 0.
Yeah, we can do that. So if num equals 0, we'll just kind of stop. And what's the recursive case? So the recursive case, we need to break down our problem into smaller and smaller chunks until we reach our base case.
Would just be countdown num -1.
Okay, so we'll just go ahead and print just for the sake of clarity. So we can print num, and then we can do what now?
Just the sorry, the function name and then num -1.
Yeah. Okay. So can you talk me through your thinking here?
It was just a guess, but just that it would call start back up at 6. So call the function again, and then it would take num -1 and go through until print num until it reaches 0.
Okay. So let's go ahead and run it. And it looks good. And if we ran this in the debugger, we would see that we have, a bunch of, every time we call this, we're putting a new stack frame on the stack. We have another one, another one. So every time we call countdown, we're adding another stack frame until we get to our base case, which is going to be the top stack is going to finish executing because it's reached the base case. And then all the other ones will pop off in turn. So does anyone have any questions about this?
Chad, what would be the difference if you returned the recursive call, the countdown num -1?
Yeah, so that's a great question. So ultimately, this is just going to return. So this is kind of so the example is maybe a little different. We'll look at another example where we actually do care about the return value. Here, we're just doing side effects. So if we were to return this, ultimately, we're just going to get none. Because the final thing we're returning is we're just returning, which means we're returning none. So this is ultimately just going to be none. We could, so we can print that. So we'll just check this out. I'm gonna comment this out. We get none. If we were to return some value here, we'll get that value. Does that make sense? This is maybe not the best example for showing that, but we'll look at a couple others where it makes more sense.
So would this work also if you did on line 14, instead of doing num minus 1 as what you're passing in as an argument, you just made a num like decrementer in the actual original recursive function? Would that still work?
Okay, so your question, so if I added another local variable here, like, can you describe what you're asking again?
Yeah, so like the main function that we're going to be calling recursively, so like the actual countdown function, if you made whatever, so num as the parameter on line 7, if you did a num decrementer, so like a num minus minus, and when you call it, it would just it would decrement automatically instead of having to do num minus 1 on 15. I was just curious if that would work.
So where would I put the num minus minus?
I guess on line 8, and then you would call it recursively on line 16 now. So if you take num minus 1 out of 16, and then so then just put num, yeah, and then so, and I was just curious if it would work if when you called it, it would automatically decrement down, and we'd still get the desired 10 through 1.
In this case, I think you would. So let's say if we start with 10, because we're reassigning it, right? So if we start with 10, num minus equals 1, so num is now going to equal 9. It's going to check this, no, and then it's going to call with 9, which means it's going to get executed again with 9 minus equals 1, so that num will be 8. So because we're reassigning it and then passing it in, it's effectively the same thing as what we were doing before. So this should also work if I run this. Let me just print this. Except where I'm printing this, but
Did it skip 10 though?
yeah,
So skip your input.
yeah,
so
our count is off, so we'd have to play this because it's, but same basic idea, yeah.
Okay, yeah, I just didn't know if that would be effective as well, or if it really is the best way when you do a recursive function to do like you originally had on line 16 and do, like num minus 1 inside the parameter or the argument that you're passing in.
Yeah, I mean, either one could work. Kind of just depends on how you want to organize it. Like, are you going to be using num anywhere else? Do you want it to be decremented first and then do that, or it kind of just depends on how you're organizing it. I wouldn't say that there's like a universal rule or anything. Okay, cool. Let's take a 5-minute break, or let's come back at 10 till. Okay. So we've just seen kind of a basic example of solving a problem that we would typically solve with a loop, a for loop, or a while loop, but using recursion instead. And there are languages where you have to do stuff like that, where you don't use for loops, and you don't really need, strictly speaking, you don't need for loops. There's not there's no problem that can't be solved recursively that you can solve iteratively, minus some limitations like, the number of stack frames you have and stuff like that. So let's look at a slightly more advanced problem. And before we do that, I'm going to solve it. We're going to solve it iteratively a couple ways, and then we'll resolve it. Then we'll solve it recursively. So the problem is I have a list of integers, and I want to get the sum of all of them. So I start off with this list 1, 2, 3, 4, and I want to get back the integer 10. So we have a few ways of doing that. Would anyone suggest one way of doing that?
Just set a total to 0, and as you iterate through the list, then you just add the numbers to that total and then return it at the very end.
Okay, cool. So total 0 is a sensible default, and then loop over it. Maybe I'll call this nums. And then what do I do here?
You're just gonna you do total plus equals n,
Okay.
and then hit enter, and then you do a backspace, return total. Yeah.
All right. So if I print this up, so I get 10, which makes sense. So this is fine. This is an iterative solution. This is like what you would call a imperative style of programming. We'll talk. We've seen object-oriented programming. There's a few different kinds of basic paradigms. This is imperative, and so imperative means it's very like detailed. Okay, set this total, set it equal to 0, then iterate over every single one, and each time reassign the value to this variable n, and then each time you're going to, reset total to be whatever total is plus n, and then you get, so it's very like, you're telling it exactly what to do in every step. So imperative style, it has its uses, but it's not the most sophisticated thing. There's another way of doing this. So there's actually a built-in way of doing this in Python. You can actually it's down. So this also works. So it just so happens that Python has a built-in for this particular case. But this is a specific instance of a more general pattern. And that more general pattern. So in JavaScript, we have a few higher order functions. So does anyone, we haven't really done much with JavaScript for a couple weeks, but does anyone know some higher order functions in JavaScript?
Like map and filter?
Yeah, map, filter, and there's another one. Reduce, yes, reduce. So what does reduce do?
I think it reduces all the numbers in a list to just one number, and so you can make it get the sum or like multiply or whatever you want.
Yeah. So reduce takes in a function and some kind of list or something, and then whereas map will give you a new list, right? So if I give map a function and a list, it's gonna give me a new list, right? And then the new list is gonna be the same length as the list that I gave it. Because it's gonna apply that function to every element in the list and give me a new list with the transformed elements. Reduce is a little different. It's not gonna give me, it's gonna give me back a single value. So I give it a list and a function and it gives me back a single value. So let's take a look at that. So in the syntax may be slightly different in Python versus JavaScript, but it's the same basic idea. So in Python, we're gonna have to import something. So from, I think it's functools. This is just what you have to do in Python. It doesn't really mean anything. And then reduce, you can look at the signature here. So this is hard to read maybe. Can anyone tell me what the signature is here?
Looks like you have to pass an iterable. That's the first argument, and then where you start from.
Yeah, it's so how many arguments does reduce take?
2.
Okay, so it actually potentially takes 3. So there's function. So this is hard to read. So Python is
Oh,
not
okay.
a statically typed language, but if you ever worked with statically typed languages, this will be more familiar to you. But it takes a function and it tells you, the function signature. So the function actually takes 2 parameters. We'll see that in a sec. But it takes a function, and there's a comma, and then the second thing is a sequence, which a list is a sequence, so that satisfies that. And then the third thing is an initial value, which we're not going to worry about right now. So the way it works is the function that reduce expects is going to have 2 parameters, and the first parameter, I can't remember what the first are, but anyway, it takes 2 parameters. I think the first one is like an accumulator, so that's the value that's going to get passed in and accumulated every time. And the second value is whatever the current thing in the list is. So that might seem a little abstract. So we can actually define a function here. So we want to add all these together. So we can call it summer, I guess. And it's going to take an accumulator, and we'll just call this the value, whatever that is. And it's going to return accumulator plus the value. And then in reduce, we'll talk more about this, but so I can pass in the function that I want, and then also the list, so nums. And if I print this out, I'll comment these out. I also get 10 here. So this is, higher order, more advanced functional stuff, but we've seen some of this stuff before. So reduce expects a function, and the function signature is 2 things. And the way it works is it's going to start iterating over nums. So I'll move that down here. You can look at it. So we pass in nums, and what it's going to do is it's actually going to start with, by default, it'll start with, so the third optional parameter is whatever you want the accumulator to start with. So if I pass in the third parameter, let's say 1, then I'm actually going to get 11. Because I'm starting the process out with 1. So if you start it with 0, which is a sensible default for adding integers, then we'll get and 10 again. If you don't pass in anything, then it starts with the first one. So just FYI. Okay, so what this is going to do is reduce is going to iterate over every element in this nums, like all these other higher order functions. And what it's going to do is it's going to apply this function summer to them, but it's going to apply basically 2 at a time instead of map where you do one value at a time. It's kind of going to do 2 at a time. So the first time through, it's going to pass in this first value or whatever we give as that optional third parameter, and then the second one. So the accumulator is going to be 1, and this value is going to be 2, and it's going to sum them up. So I'm going to get 3 here, right? Then it's going to move on to the next one, and the accumulator is going to be whatever the previous sum was. So in this case, it's 3, so that's 1 plus 2. And then the value will be the current thing that it's on, which is 3, which is going to give you 6. And then next time through, this accumulator is going to be 1 plus 2 plus 3, which is going to be 6. And the value is going to be 4. So I'll get 10 here. And then it's going to ultimately return whatever this accumulator is. So that's how reduce works. That's how you go from some kind of iterable, like a list, to a single value. All right. So we've seen
Sorry.
Yeah.
Sorry.
Go ahead.
Could you also use reduce with the lambda function?
Yes, you can. So here we're defining our own specific, named function. We could also do the same thing with a lambda. Has anyone seen lambda functions in Python? Okay. Elijah, I see you nodding. Can you tell me about lambdas?
So lambda is kind of like where instead of putting in like in this case for reduce, you put in summer and it'll pass through that function. Instead, you could kind of like define your own function on the spot. I believe it's kind of like writing your own custom function, but passing it into another, like a statement, I guess.
Yeah, good. So it's used. So not everyone thinks lambdas are a good idea necessarily. There's some, I forget. Anyway, I'll find it and paste it in the chat. But there's some joke about lambdas in Python. So I have a named function here, like a normal named function I can pass in. If, for example, I just have so this is a very simple function. All I'm doing is adding 2 numbers. So if I could potentially inline this if I don't need to use it anywhere else. I'm not going to use this adder thing anywhere else. So I could do lambda, and then the 2 parameters, and then a colon, and then whatever I want to return. So this is just like a JavaScript arrow function, right? The syntax, I have to call it lambda, and then whatever parameters I want here, separated by comma, if there's more than one, and then a colon, and then whatever I'm going to return here. So there's some limitations. This has got to be 1 line, right? In this case, that's fine. So this will also work. So now I don't need this anymore. And that works fine. So you can either pass in the name function, summer, or you can kind of inline it. And either one works. Okay, so we have lots and lots of ways of adding up everything in a list, but it's all iterative, which is fine. But we can also do it recursively. So let's take a look at how we can do that recursively. So I'm going to take this and put it down here. So this is going to be a slightly more complicated problem. So than the previous one. So with the countdown problem, for one, we were only interested in the side effect, right? We just wanted it to print. So we didn't really care about return value. In this case, we are going to need a return value. And we know we're going to take in a list and we're going to return an integer. Now, when you think about solving a problem recursively, your knee-jerk reaction is just going to be, I need a base case and I need a recursive case. So I'm just going to mark that here. Actually, let's try the functions on def. Going to take in a list of nums, and I'm going to have a base case. Let's do pass for now. Okay, so my base case and my recursive case. So our recursive case, we know that every time we call it, we want to be breaking down our problem domain, which in this case is this, our nums. We want to break that down into smaller and smaller chunks until we reach our base case. So what is our base case here? That's it's not always, entirely obvious. There might be, in this case, I think you could make an argument that there's a couple different possibilities for a base case. But when you're thinking about a base case, in general recursion, you want to be thinking about what is the simplest possible input I could have. What is the simplest possible input that I can have? Because recursion is, I want to take a simple solution and just apply it over and over and over and over and over again. So in this case, if nums were just a single item, what's the sum of a list of one item?
The item.
One.
Yeah. So I mean, it's kind of trivial, right? It's kind of stupid in a way, but I think that's the simplest, kind of the simplest case, is that if I have a list of one item, a single item, then I'm going to return that thing. So the sum of a list of 5 is 5. The sum of a list of 20 is 20. The sum of a list of 1 is 1. What if I give it an empty list?
Then just return 0.
Yeah, I think that would be a sensible default as well. You could return 0. So that's, you could make an argument about that, and so maybe our base case is the empty list where it's 0. But just for the sake of simplicity, I'm gonna stick with this. But you could definitely make an argument. So there isn't always just one base case, is what I'm saying. So in this case, I think our base case, I think we can define that. So if when nums is 1, return nums 0. So let's go ahead and run it. This should be fine because this is going to hit. Let me print this. Okay, so it looks like this will work for now. So the recursive case is going to be a little tricky. So let's look at we'll try to keep our example as small as possible. So if I have 4 here, first off, I'm expecting 5, so I know that. So what's my recursive case going to be? So if I pass in 1, 4, I know if it's just 1, then I can just return it.
So do we need to like pop off in the recursion? We need to be popping off on the list.
Yeah. So if we know that our base case is a list of 1 element, then at the very least we know a recursive case is we're gonna have to like move towards a list with 1 element. So at the very least we know we're gonna have like we're gonna have to shorten our list somehow. So maybe I'll just make a note of that. Because if we don't shorten our list, then what's gonna happen?
You never hit the base case. No.
Yeah, we're basically, you might as well not have a base case because you're not working towards it at all. So we're gonna have to somehow shorten the list. So this is not the right answer, but maybe kind of a minimal part of the right answer is we can call recursive sum with nums and so what is this?
That's slice. That's slice.
Slicing the first.
Yeah.
So it starts at 1 and it goes all the way to the end.
Yeah, exactly. So it's basically I'm creating a new array minus the first element. So I'm shortening this by 1 every time. So if I call this, I'm not going to get the right answer, but I'm not getting an infinite loop. So that's something. So I'm pretty sure my base case is correct. Let me not have that pass in there anymore. Pretty sure the base case is correct. And I know that at minimum in the recursive solution, I'm going to have to be returning a shorter and shorter list every time until I reach a list of length 1. What else do I need to do?
We need to store our sum, or we need to store our ongoing count.
Yeah. So this is kind of tricky. There's a couple ways we could do this. I want to try and well, let's try it this way first. So you should never ever do this. This is very bad. But let's create a global variable called total. So if I had this global variable total out here, how would I solve this problem?
You'd update total as you went through your each recursive loop.
Okay. So I would update the total with what though? How would I actually do that? So I call recursive sum, in this case, this is just doing a side effect. So side effect doesn't have to be just printing. In this case, I'm changing something outside of the function. So this is a side effect. So we're gonna change this, but for now.
The way you had it first time, I think would work. It was just you'd have to remove that value after you update your total with it.
Okay, so I pass in this list of nums 1, 4 recursive sum. So this is 1, 4. This condition doesn't happen. So I'm going to hit my recursive case. What do I do in my recursive case? So I have a list of nums is 1, 4.
So I think if you run pop on it, that returns the value, and then you add that value to total.
Okay, so I could do that. I could do, let's do, nums dot pop, and then total plus equals last, and then call recursive sum with nums. So pop will modify the original list, right? So we'll.
But we need to actually remove it. Huh? Well, because does pop? I can't remember. Does pop remove it from the
Yeah.
list? Because we have to remove it too. Okay, cool.
Yeah, it does. And so we'll print total, and we're expecting total to be 5. So let's see if that works. Local total reference of 4 assignment. So this is a Python quirk, I guess. Unbound local error. So you may first you shouldn't encounter this error because you shouldn't be doing this. But if you do, we have a global variable that we're using here. So we just have to mark it inside the function. So I'm going to do non-local total.
So wouldn't you just instead of having total, just add the number you pop to index 0 of nums?
One sec. Do I have mark this global? Just try that. Yeah. Okay. Sorry. What was your question?
So instead of having a global variable, wouldn't you just add the number that you pop to index 0 of the list that you're working with?
Add it to index 0.
Yeah, so like, I mean, you want to add 4 and 1, right?
Yeah.
So wouldn't you just pop off 4 and then always just add it to index 0, which would be 1, and you could just do that through the whole list, and then you don't need a global variable?
Can you say? I'm not entirely sure.
Yeah. So I mean, and maybe I'm thinking of this completely incorrectly, but you've got your list and it's 1 and 4 right now. So
Yeah.
you pop off the last number of the list, which in
Okay.
this case is 4, and then
Right.
just add that number to index 0 of the nums list, which is 1. And then you can just do that because the nums number 1 would just be that total, and then you could just keep doing that over and over, right?
But if I added
7, then you would just add 7 to 1, and then the next time it's called recursively, it would just be 4 plus 8, because it would pop off the last and then add it to the. Is that not right? I mean, I don't know.
I'm trying to think. So if I so we remove the last one. So we remove 7.
Yep, and then add
it
it to 1.
Oh, so we add it to, okay, so we add it to 1 here. So we add to whatever
then-
the first element is here.
Yeah, and then so then now the first element's 8, and then so then
But-
you just pop off 4 and then add it to 8.
But the first element is 8. Where is that coming from? Are we modifying
7 plus
num?
1? Yeah, you'd have to, yeah.
So you pop off the last one, you add it to whatever the first element is, and then reassign the first element.
I guess you would have to, yeah.
Yeah, I mean that.
I was just thinking, and you wouldn't have to have a global variable.
Yeah. I think we still would have to have a global variable if we had, a list with 1,000 elements on it. Yeah, so I mean that's a good idea, but we're also kind of violating the implicit constraints, which is that our we should really just be doing one thing basically. We can start doing all kinds of stuff where, okay, I'm going to modify this and add this and change that. But so yeah, that's definitely a good solution or a good way of thinking about it. But I'm trying to solve it in a particular kind of way. So what we have right here also doesn't work because we're just returning here. So we could tweak that, but I don't want to spend too much time on what I think is not a very good solution. So this would kind of work. We take the last element, we add it to the total, and then we call recursive sum, and then maybe here, instead of just returning, we add whatever that is to total. So we could do something like that, like So this should give us 5. So that works, but we don't want to do it that way anyway. So I'm gonna get rid of this, get rid of the total. So we're not allowed to do that anymore. So the problem is, so we know what our base case is. We know we're gonna have to remove some, at the very least, we have to remove an element from here. But we also, there's something missing, right? If we have a global variable, we can like track that storage, right? We can increment it, change it every time. But here we don't have access to that. We don't have access to another variable.
Can we add a parameter there that would store it for us?
We could, yeah. So that's another way of doing it. Maybe we can look at that. I guess we could do that now. So this is a variation on the global variable, except we're keeping it within the function. So it's still a local variable, so it still is following the rules. So you can add this here. You can do total equals 0. Add this as a default parameter. And then we could potentially do the same stuff we had before, which is so we could pop off the element. So last, or I'm not even sure we have to, yeah, we can do that. So last equals nums dot pop, and we do total plus equals last. And then we call recursive sum with nums, which has been modified, and then whatever our new total is. And then here, we wouldn't return nums 0, we would return total. So let's print that out. So I'm getting none here. So why am I getting none?
Is there no return?
Return.
Yeah.
Sorry, I couldn't hear that. Okay, so the issue is that, yeah, I'm returning here, but I'm not returning here. So return, and that gives us 4, which is not correct. So let's see. So I'm gonna have the same issue here, or I either need to change my base case to length is 0, and then I can do that. So that would work. Well, I guess we'll go ahead and finish that. So we'll return, let's make the 0. And this works. So this works, and we're not using a global variable. So that's good. So we have a recursive solution. I'm gonna try and show you another way of doing it. Where we don't need this. So I'll just copy that and make a new one. Copy all this to. Okay, so we still have our nums 4. All right, so we want to do something similar, but I'm going to get rid of this additional variable. I'm going to go back to this as 1. Go back to, oops, back to where we were. Okay. So I've got my recursive sum. I know my base case is that if I have a single element, I just return that because the sum of a single element is going to be the single element. And then the recursive case, what I'm going to end up doing basically, so here we're creating our own value and we're continually updating it and passing it into a new function call. So that works. There is a way to do that where we kind of rely on the call stack to track this for us. So we're not going to be able to really see the value necessarily, but we can rely on how it, on how the call stack works to store that value for us. And the way you can do that is I can call return. So what I want to do is add, right? I want to take whatever the first element is. So there's a couple ways to do it. We could stick with the pop stuff. I'll just do that last. Equals. So now we have this value, which could be the first or last. We'll just do this because it's a little bit more explicit. We could also use the other syntax, which is a little cleaner. And then what I want to do is I'm going to take last and add it to whatever gets returned from calling recursive sum with the remainder with the remaining values in the list. So that's kind of the conceptual trick here, is that I'm postponing what I know here. So I'm saying, I know that my base case is if it's a single element, I return that element. And then here I'm saying, I want to add the first element in this, or in this case, the last one, so whatever, but 4 plus, and then whatever this is. This could be 1,000 items or 1 item or 1,000,000 or whatever, it doesn't matter. But it's whatever this is going to return. I know that ultimately this is going to return a single integer, right? Because that's my base case. And I'm working towards the base case because I've shortened the list by popping something off. So I kind of trust that eventually this is going to resolve to an integer. So I should be able to add whatever this is to whatever this resolves to. So let's see if that works, and then we can kind of like draw out how that works. So nums. So this gets us 5, which is the correct answer. We can add another element. And that gets us 12. So yeah, we could write more tests, but it looks like this is basically working. So let's look at this case. So 147. We'll just walk through it, manually. So I'm calling recursive sum with 147. So nums is now 147. I look at this conditional, it doesn't apply, so I keep going. So I'm going to pop this 7 off. So now last is going to be 7 and nums is going to be 1, 4. So what I'm saying is take 7 and add it to whatever the result of applying recursive sum 2 to 4 to 1 and 4 is. So we're kind of like branching off our solution. So I know, so the first call is going to say, if the first call kind of has to hang out and wait for an answer here. So I know that this one, I'm going to add this to whatever this is. I don't know what this is, so I'm going to pass it off to you. So this is going to be recursive sum with 1 and 4. This is happening on a new branch. So I can look at 1 and 4. I check this. This doesn't apply. So I remove the 4. So I'm going to return 4 plus whatever the recursive sum of 1 is. So then this is going to get called again with 1. In this case, our base case does hit, and it returns, it actually returns a single value, which is going to be 1. And once that happens, that stack gets popped off, and that returns a value to the previous stack, which can then resolve, and so on. So it just like everything trickles back up. So we'll let me write this out just so you can kind of see what's happening. So we start off with 1, 4, 7, and then we're going to call it. So the first time we call it, last is going to be, so it's going to be 1 plus whatever the sum of 1 and 4 is. Or sorry, 7 plus. 7 plus whatever the sum of 1 and 4 is. But I don't know what this is not a value. I can't add 1, 4 to 7. So this 1 and 4 is now going to kind of break off on its own call stack. This is happening, in parallel. So I have 1 and 4, and this is going to get broken off into 4 plus the array of 1. And I still can't add these, right? I can't add, a list with 1 in it to 4. So I'm gonna have to break off. This is gonna get called again, recursive sum 2, with just that in it. So this will be 1, and this is gonna return 1. So now I've reached my base case. I've returned this single element. So now I can like work my way back up. So I now know that this equals 1, right? And with that knowledge, I can go back up into this other stack and say, oh, well, I know what this is now. This actually equals, so 4 plus just 1, right? And I can take that, and now I know that this equals, let's just say this 5. I know that the array 1, 4 equals 5, which means that I can now resolve this. So I'm going to jump up here and say that it's 7 plus 5, which means that I know that this array here, 1, 4, 7, is 12. So it's it's weird. It's a weird way of thinking about it, but it's a problem that is actually one simple problem applied over and over and over again. And that's kind of where recursion shines or is useful. There are other cases where some problems are definitely recursive problems, and some are you could solve it recursively or not. This is kind of this is not a problem that like screams you need to do recursion, but so does that make I'm reluctant to ask, does that make sense? Because it's a bit weird. But does anyone have any questions about that so far?
I think actually this was really clear, very, very easy to understand the way you explained it just now, for me.
Okay, if you don't feel that way, that's also perfectly fine. So let's go ahead and we'll just look at this in the call stack, just to maybe confirm what we think we know. So here we go. We're gonna call recursive sum with 1, 4, 7. So we jump in here. This is gonna nothing should happen basically, and then we're gonna end up making another call here. So we've we've called this, so now we're in it. We're in the first call to recursive sum, and we can see we can kind of track where we are by looking at this. So nums is 147, so we know we're in the first call. So this condition isn't going to hit. I'm going to remove that. The last is going to be 7. Nums is going to be 1, 4. And then this is going to do last, which we know what this is, plus something that we don't know. So we're going to have to wait for this to resolve. We're going to pass this off to the next call stack. And we can see that this call stack is still kind of, it has its own state saved, right? That's what a call stack is basically. It's just, it's just saving its state right now. But this, in order to get this value, we have to create a new call stack, which has its own local variables. And we're gonna have to run this. In this case, we can't resolve it, so we're gonna have to call this again, which means we're gonna create another call stack to resolve recursive sum with 1. We call this again, we create another call stack, and we can look. You can look here. Actually, this is not saving. Yeah, nums is not saving. Anyway, yeah. That's fine. So we can still see that we're in that third call stack right there. So nums 1. So this condition is actually going to hit. So I can actually return that 1 now, which means that I can pop this off of the stack. So I pop this off of the stack, which means that this can now resolve. So I have 4 plus that most recent return value, which is 1. So I can resolve that, which means I can pop that stack off. So now I'm back at this topmost level. So I have and I call that, excuse me, I call that, and now I've added them all together, and I can finally return. So here we're basically using we're using the call stack. So it's tricky when you're writing this or thinking about this, because you're basically, you have to kind of defer. You can't really see it in your code what the answer is. You're basically saying, I'm going to take this and add it to whatever this results to. And I have to kind of trust that I'm doing 2 things. 1, I'm breaking down my problem domain towards the base case. And 2, that the base case is going to return a value which is going to be, make sense with whatever else I'm doing here. So in this case, I know that eventually I'm going to break down my problem domain to a single integer, which I can then add. So I'm taking an integer plus an integer. So that makes sense. I know I'm allowed to do that. I just don't know yet what this is going to be. So I'm deferring it. I'm passing the buck to the next call stack. And it's like, okay, call stack, I know, I'm trusting you that at some point you're going to give me an integer that I can add to whatever I'm doing here. And that can keep going, obviously. So if this were, 1,000 elements or 2,000 elements, we would have an issue with Python, but that's anyway. So are there any more questions? That's basically that's it for the lecture.
Chad, if you put that function into pythontutor.com, I think it breaks down the recursive steps a little more clearly, I think.
Okay, cool. Yeah, if you could post the link in the Slack channel so we can see that. Thank you.
Can you build an array or a list like this? So instead of going down to a base case of 0, can you create something going the other direction? If that's a complex question, then just ignore it.
Yeah, you can definitely do that. Yeah, I mean,
or would it make sense to do that, I guess, or to be better to do it another way?
It depends. I mean, there are questions about like efficiency, which I wouldn't worry about right now. We're we're trying to learn the concept of recursion. But in practice, you know, some languages are better at recursion than others. We don't have to worry about the details, but you know, Python is not one of those languages, so I wouldn't use recursion as just a default with Python. There are other languages where, you know, you could and should. But yeah, there's no reason that you couldn't build up a list recursively. And if you want to try that, that would be a great exercise. So go for it. And if you do have a solution to that, then you can post it in the Slack channel as well.
Cool. Thank you.
All right. Let's stop.